Mr. Harris here, and welcome to another video of Unit 9. In this video, we're going to talk a bit more about giant ionic structures, and we'll be doing some examples together. Before we begin, I'd like to introduce you why we need to learn about the properties, the structures, and the bondings. So for example, let's look at the diagram over here. My question is, why does copper conduct electricity in solid state? Why can't the other three? Or why are some of these substances having a high melting and boiling point while the others do not? Or why are some of them hard? Why are some of them soft? So all these questions, you guys will be able to answer them once we finish this unit. Okay, let's begin. In the previous video, I talked about giant ionic structures. And one example that I used was of sodium chloride. So if you guys recall, sodium chloride, it has a lattice structure where the ions are basically alternating with one another. So left, right, top, bottom. However, there's one point that I would like to raise in this video is that not all ionic compounds, they would have the same structure. For example, let's look at the structure of cesium chloride. So let's look at the diagram on the right. So cesium ion, the one that is in purple, this one, is surrounded by 8 chloride ions, the ones in green. While each chloride ion is also surrounded by 8 cesium ions. So do you notice that it is the structure, diagram A over here, is a bit different from what you've seen in structure A of sodium chloride. So not all ionic compounds, they would have the same structure, okay? Another thing we learned last time was about the 4 different properties of ionic compounds. So the first property we talked about was the melting and boiling points. We also talked about the physical state. We also talked about solubility. And finally, the 4th property we learned was about electrical conductivity. Now, if you recall, ionic compounds, they have a high melting and boiling point. What was the reason? Yes, it was due to the presence of strong ionic bonds. So if you don't remember, you can refer to the previous video and watch for the explanation. We also learned about how ionic compounds, they are hard and they're solid at room temperature and pressure. And we also learned about them being brittle. I use an analogy by using a hammer. So you can look at watch the previous video to get more information. Solubility, we learned about how some ionic compounds, they're soluble in water. Okay, and finally, we learned about ionic compounds, they're able to conduct electricity in molten and aqueous states. What was the reason? Yes, because of presence of mobile ions. Yes, mobile ions. Okay, so just to summarize, ionic compounds, they're hard, but they were brittle. They have high melting and boiling points. Some of them are soluble in water. And finally, they conduct electricity. Not in solid state, but in molten or aqueous state. Okay, so let's do some practice together. You can pause the video and read the question by yourself. So pause the video right now while I'll continue. Okay, let me go ahead and read. Cesium is a group 1 metal in the periodic table. Group 1. It combines with iodine to form cesium iodide. Ionic bonding exists in cesium iodide. Yes. Question 8. Draw the electron diagram of cesium iodide. Okay, that's simple. We also did this in the exam. So iodine is group 7, cesium is group 1. So let's go ahead and draw it out. Cesium, it will give one of its electrons, so it has a positive charge, whereas iodine, because it's in group 7, so I'll go ahead and draw 1, 2, 3, 4, 5, 6, 7, and cesium will give one of its electrons. And don't forget to put down the overall charge, negative. Okay? Cesium iodide. And how can you be sure that ionic bonding exists? Remember, I told you usually it will be between a metal, cesium is a metal, and iodine is a non-metal. Okay? Most of the time is in this case. However, there are some exceptions, and I've talked about them in class. Alright, let's continue. Question B. Electrolysis is an experiment which you can perform using an aqueous solution. Let me go ahead and highlight that. Aqueous solution of cesium iodide to provide evidence for the presence of ionic bonding. Draw a label diagram of the setup that you can use for this experiment. Okay, I'll pause the video. You pause the video and enjoy it by yourself. I'll continue. So the label diagram will look something like this. Make sure that you label the light bulb and the solution that you were using. Okay, now my question is, why does the question state so obviously that we're using aqueous solution of cesium iodide? Yes, it's giving us a hint that there is or there are presence of mobile ions. Yes. So because there are mobile ions present in the solution, the light bulb is able to light up. Okay, let's go ahead and read. Suggest how your result can show that the bonding is ionic. So in other words, it's asking how could you show that there are presence of mobile ions. So as I've just mentioned, if there are mobile ions present, the light bulb will light up. Okay, let's go ahead and write that down. The light bulb lights up. Okay, question 3. Discuss with explanation the electrical conductivity of cesium chloride with reference to the type and property of particles in it. Okay, so it's asking about cesium iodide in general. So it's not asking you specifically whether it's solid state or molten or aqueous state. So in this case, you will need to mention about both. So in solid state, can cesium iodide conduct electricity? No. Why? It's not a conductor because, yes, there are no mobile ions present. How about in molten or aqueous state? Yes, it is able to conduct electricity because mobile ions are present. Of course, you'll need to write it down in full, complete sentences. I'm writing it just a short form so it's easier. Okay, so here's the full explanation. Cesium iodide does not conduct electricity in solid state because ions are not able to freely move. However, in molten or in aqueous state, ions are able to freely move. Let's move on. Okay, this is on page 185. So you can go ahead and do it by yourself first and then come back to this video and check your answers. But I'm going to go ahead. Magnesium reacts with oxygen to form magnesium oxide. Question A. Describe what happens in terms of electron loss and gain when magnesium atoms combine with oxygen atoms. Okay, let's see. So magnesium, let's go ahead and write down the electronic arrangement. So magnesium is 282. How about oxygen? Oxygen is 2 6. Okay. So you're asking us in terms of electron loss and gain. So for magnesium, in order to achieve a stable electronic arrangement, it would need to lose 2 electrons, right? Two electrons. How about for oxygen? How can it be stable? Yes, it would need to. Oxygen would need to gain 2 electrons. So it becomes 2 8. Okay, so let's go ahead and read it. As I mentioned, magnesium atom would need to lose 2 electrons, while oxygen would need to gain 2 electrons in order to obtain a stable outermost shell of 8 electrons. Okay, you can read it by yourself. Let me ask another question. Okay, just an extra question. Can you draw the electron diagram? Just an extra question for you. Can you draw the electron diagram? Can you pause the video right now and do so? Okay, it'll be fairly simple. So Mg, you have 2 plus over here, and oxygen. So 1, 2, 3, 4, 5, 6, and it gets 2 electrons from Mg. And don't forget to add 2 minus. Okay, so that's the electron diagram of magnesium oxide. Okay, let's go to question B. Give the chemical formula of magnesium oxide. So fairly simple, you only see one Mg and one O, so MgO. So I've posted a video on how we could name ionic compounds, so you can also check out that video. Okay, let's read question C. Let me go ahead and rub this out first. Magnesium oxide is used to manufacture heat-resistant bricks for furnace linings in the steel-making industry. State and explain the property of magnesium oxide that makes it suitable for this use. So it's asking for the property. So we learned about 4 different types of properties, right? Solubility, physical state, melting and boiling point, and electrical conductivity, right? But in this question, they're asking about heat-resistant bricks. So can you identify which property is it asking about? Yes, it's asking about the melting and boiling point. So the question is asking, why is magnesium oxide suitable in this case? Why is it suitable for manufacturing heat-resistant bricks for furnace linings? And we need to relate it to the property of magnesium oxide. So let's look at the property that magnesium oxide has. Does it have a low or high boiling point? Yes, it has a high boiling point. Why does it have a high boiling point? Because there are presence of strong ionic bonds. Yes. Okay, let's have a look at the answer. So it has a high melting point, okay, because there is a presence of strong ionic bonds. Okay, so that's the end of this video. Hope you get a better understanding of what giant ionic structures are. In the next video, we'll be talking about giant covalent structure. So make sure you will watch those and please subscribe to the channel so whenever there's a new video out, you'll be able to watch it immediately. Okay, see you in the next video. Bye.